We humans often learn generalizable constraints over tasks from the demonstration. However, finding a constraint is an ill-posed problem due to multiple possible reward and constraint pairs. We introduce Transferable Constraint Learning (TCL) that jointly infers a task reward and task-agnostic constraint via additive reward decomposition. Our method takes demonstrations and a task reward candidate as input. The inverse reinforcement learning process finds a total reward. The reward decomposition process finds a task reward from the given reward candidates. Then we can use the complement of the task reward as a soft constraint that can be transferable to other purposes of environments. We investigated the decomposition performance of our method and baselines in a 2D navigation environment. Our method shows a reward map of successfully recovered constraint that is close to the ground truth one. Our method also shows the inferred constraints or the successfully decomposed results, showing less correlation with the ground truth task rewards. We tested our method on simulated tray carrying task environment. Here we want to recover a constraint that restricts the angular difference to be in 15 degrees. Our simulation results show TCL finds a constraint transferable to novel configurations, leading to successful task completion. However, baseline method either fails to reach the given goal or fail the object. We further tested our method on a reaching task with a wall-falling constraint. In this environment, the agent needs to keep a distance of between 0.1 and 0.15 meters from a wall. We can observe that TCL finds the wall-falling constraint transferable to a new environment with a sinusoidal wall. On the other hand, baseline methods such as ICRL result in an agent that violates the wall-falling constraint. Finally, we tested our method to another reaching task with a normal force constraint. In this scenario, the agent is required to exert a normal force greater than 0.8 Newton. The result shows that TCL successfully adapts the normal force constraint to a novel sinusoidal ground environment. However, baseline method failed to generate agents that follow this constraint in a new environment. Obtaining 16 demonstrations, we trained our method TCL in a real-world environment. For experiment, we have used the motorized reset mechanism that automatically overrides the target object. After 2 hours of training, our algorithm converged and succeeded to imitate the carrying behavior. We trained our method TCL with randomly sampled configurations. Over training time, our method starts to show enhanced performance constraining the angular difference. Our method robustly and successfully reproduced the demonstration-like safe behavior, while the baseline method failed to reproduce it. We conducted additional real robot experiment on a wall-following environment. In this environment, a tool-attached robot moves the ball along the curved wall. To deliver the ball without dropping or hitting the wall, the robot should maintain the distance from the robot to the wall between 9 cm to 11 cm. To expedite the learning process, we use a simulated wall-following environment in a Box 2D simulator. We collected 16 demonstrations and used our method to recover the constraint. We transferred the constraints, which learned by TCL in simulation, to another simulated environment with a new wall. We then transferred the learned policies to the panda arm in the real environment with a new wall shape. We found TCL successfully delivered the ball, moving it along the curved walls, while maintaining the precise displacement constraints.